Welcome to lecture 33 on essentials of topology. In this lecture 2, we will study the concept of homeomorphisms. Begin with the concept of homeomorphisms. In the previous lecture, we have seen that whenever we are talking about a homeomorphism from a topological space x tau to y tau dash, we have seen that this f should be a bijective function plus this should be bicontinuous in the sense that this f is continuous and f inverse is also continuous. When we talk about the continuity of f inverse, which is a map from y to x, what we have seen that if these are the sets x and y and f is a map, then if we are taking any open set here, let us take this is h. So this h is tau open and continuity of f inverse means let us find out inverse image of this h under f inverse. It should belongs to tau dash or this f inverse take its inverse h is tau open or tau dash open. But at the same time, because of the bijectiveness, we can say that this is f h, that is image of h under f is tau dash open. So what precisely going on that instead of computing inverse of f, we are finding out the direct image of this h, that is f of h, and if this h is tau open and f of h is tau dash open, that is equivalent to say that f inverse is continuous. The functions sending tau open set to tau dash open sets are also known as open functions. Thus, in this lecture, we will study the concept of or the characterization of homeomorphism in terms of open functions. And when we are talking about open functions, question will come, what about closed functions? So we will also discuss about it. We will discuss the possible relationship, if any, between open and closed functions and their characterization in terms of interior as well as closure. Begin with, let x tau and y tau dash be topological spaces and a function f from x tau to y tau dash. We say that this function is open if image of each tau open set is a tau dash open set, and this function is closed if image of each tau closed set is tau dash closed set. What exactly? Actually, if we are having two sets or two topological spaces, x tau and y tau dash, let us take that this is x and this is y. So the function is open means if we are taking any open set here, if G is open, find the image of it and its image should also be open. Similarly, if we are talking about closed function, let us take a closed set here. Let us take that this f is tau closed, and if we are computing its image, that is f of f, this should be tau dash closed. Let us take some of the examples of open and closed functions. Begin with the first example. Let us take a function. This is an arbitrary function from a topological space x tau to y tau dash where this tau dash is discrete topology. Note that this f is an arbitrary function. Now, if we are taking any g belongs to tau, what about f of g? This is a subset of y. Note that the topology on y is discrete topology. Therefore, fg belongs to tau dash 2. Therefore, f is an open function. Also, let us take a closed subset of x, that is, if we are taking this f as a tau closed subset of x, then what about f of f? That will always be subset of y. And if this is subset of y, note that the topology on y is discrete. Therefore, f of f is tau dash closed, or we can say that f is a closed function. So, the example which we have discussed here, the function f is both open as well as closed. Let us take another example. This is, for example, we are taking this open interval 2, 3. This is subset of R. Let us take R cubed with low Euclidean topology. So we are assuming 2, 3 as a subspace of this R with Euclidean topology. Now let us take inclusion function from this open interval 2, 3 to set of real numbers. Note that in case of sub-relative topology, the open intervals of the form AB, where A and B are from R, will be open with respect to the topology on this open interval 2, 3. And because we are taking this is inclusion function, we can say that the image of this open interval, that is image of any open interval AB under this I, that will be AB, and this is the member of Euclidean topology. Therefore, I is an open function. It is to be noted here that this 2, 3 is also closed with respect to the relative topology. But note that if we are finding out its image, that is image of this open interval 2, 3 or closed set with respect to relative topology, this will always be this open interval 2, 3 which is not closed, or which is not tau e closed, that is not closed with respect to Euclidean topology. Therefore, this inclusion map is not closed map, or this is not a closed function. So, the example of this inclusion function, this is an open function but not a closed. Let us take one more example. Let us take a function f from real line with Euclidean topology to this R with Euclidean topology, and let us take this function as a constant function for all x belongs to R. Note that this function is not open, but it is closed. Why this is not open? Answer is, for example, if we are taking this 2, 3, this belongs to Euclidean topology, but if we are finding out its image, that will be a singleton set C, which is not open with respect to this Euclidean topology. Therefore, this function is not open. But if we are taking any closed subset with respect to Euclidean topology, that is f e tau e closed, and the image of this f under this f function f is singleton set C, which is always tau e closed. Therefore, this function is a closed function. So, we have discussed a number of examples, and what we have seen that a function may be open and closed both. A open function may not be closed, and a closed function may not be open. Moving ahead, let us discuss some examples regarding open as well as continuous functions. What we can show that we can construct some functions which are open but not continuous, and at the same times one can also construct some functions which are continuous but not open. Now let us take the first example. This is a function f from R with Euclidean topology to R with lower limit topology such that f of x is equal to x for all x belongs to R. Then if we are taking any g belongs to tau e, what about this f of g? That will again be g. That belongs to this lower limit topology, as we know that Euclidean topology is coarser than lower limit topology, and therefore this f is open. But note that f is not continuous, because if we are taking this semi-open interval 2 3, this belongs to lower limit topology, but the inverse image of this 2 3 under f is again the same semi-open interval, which is not member of Euclidean topology. So this is an example of a function which is open but not continuous. Let us construct another function from this example itself. Let us take a function f from R with lower limit topology to R with Euclidean topology, and again we are taking the function as an identity function for all x belongs to R. Now if we are taking any g belongs to tau e, that is g is open with respect to Euclidean topology, and we are computing f inverse g, that will be g, and that will again belong to lower limit topology with the same justification as Euclidean topology is coarser than lower limit topology, and therefore this f is a continuous function. But if we are taking an open subset of R, that is this 2 3 again semi-open interval, this belongs to this lower limit topology, but f of h is equal to h, that is semi-open interval this 2 3, which does not belong to this Euclidean topology, therefore f is not open. So what we have seen? We have seen that there may be functions which are open but not continuous, and there exist functions which are continuous but not open. Even we can construct some functions which can be open and continuous both. Moving ahead, finally we can characterize homeomorphisms in terms of open and closed functions. The characterization is given by this theorem that if we are having a bijective continuous function f from topological space x tau to topological space y tau dash, then f is a homeomorphism if and only if f is open, and or if and only if f is closed. The justification is simple because we already have a bijective continuous function with us. In order to justify it, if we are beginning with a homeomorphism f, it means that this is bijective continuous, which is already given, plus one additional thing, that is f inverse is continuous. Note that f inverse is continuous. This is equivalent to say that inverse of this g belongs to tau dash when g belongs to tau, and this is equivalent to say that fg belongs to tau dash, and this is equivalent to say that f is open function. So f is a homeomorphism if and only if f is open. Now if we are assuming that f is open, we can justify that f is closed and vice versa. Now let us assume that f is open and let us take a subset f of x which is tau closed. Now if this is tau closed, we can say that this x minus f is tau open. Because this function is open, therefore f of x minus f is tau dash open. As the function is bijective, we can say that this is equal to y minus of f is tau dash open, or this f of f is tau dash closed, or simply f is a closed function. Similarly, if we are taking f as a closed function, we can justify that f is open. Moving ahead, let us see a characterization of a closed function. If we are having two topological spaces x tau and y tau dash, then the function f from x tau to y tau dash is closed if and only if closure of fa is a subset of f of a closure for all a subset of x. The justification is simple. Let us assume that this function is closed. Now what we have to do, that we have to prove that closure of fa is subset of f of a closure. In order to justify it, as we know that a is always subset of a bar, and this is true for all a subset of x. Let us take the image of a and a closure. So fa will be subset of fa closure, or if we are computing closure, this fa closure will be subset of closure of f of a bar. But note that because this function is closed, a bar which is subset of x, this is tau closed, and if this is tau closed, f of a bar is tau dash closed because of closeness of f, and therefore closure of f a bar is equal to f of a bar. Thus what we can conclude here, that closure of fa is subset of f of a closure. That's the proof of it. In order to prove the converse part, let us assume it and try to justify that f is a closed function. In order to prove that f is closed function, let us take f is tau closed. We are assuming it, and we have to show that f of f is tau dash closed. In order to justify that this is tau dash closed, it is enough to show that closure of f is equal to f of f, and this is equivalent to these two statements that justify that f of f is subset of closure of f and also justify that closure of f is subset of f. This always hold, as A is always subset of A closure. In order to justify it, let us use the assumption which we have with us, if we are replacing this A by F, then we can get F of F closure is subset of F of F closure. But note that we have already assumed that F is tau closed, and because of it, closure of F is equal to F, and therefore we can write closure of F is subset of F of F. That's the justification of this statement, and therefore closure of F is equal to F of F, and hence this function is a closed function. Moving ahead, let us see another characterization of homeomorphism. Just recall, we have already seen the characterization of a continuous function in terms of closure. Also, we have seen the characterization of closed function in terms of closure. It is natural that by combining these two can be characterized homeomorphism in terms of closure. Answer is yes, and given here. If we are having two topological spaces x tau and y tau dash, and let us take a bijective function, then a function f from x tau to y tau dash is a homeomorphism if and only if closure of fa is equal to f of a closure for all a subset of x. Note that what we have already studied, we have seen that the function f is continuous if and only if f of a closure is subset of f of a closure for all a subset of x. Also, we have seen that f is a closed function if and only if closure of f of a is subset of f of a closure for all a subset of x. Note that we have already assumed that the function is bijective. So, homeomorphism meaning is that this is continuous plus closed, and if this is continuous and closed, this is combination of two statements that f of a closure is subset of closure of fa, and closure of fa is subset of f of a closure for all a subset of x, and this is equivalent to say that f of a take its closure is equal to f of a closure for all a subset of x, and that is the proof of this theorem. Similar to the concept of characterization of closed function, we can characterize open function. We have seen the characterization of closed function in terms of closure. Obviously, as open sets are defined in terms of interior, so we can justify or we can characterize an open function in terms of interior. Let us see the characterization. The characterization is given by this theorem, and the statement is, if we are having two topological spaces x tau and y tau dash, then a function f from x tau to y tau dash is open if and only if f of a interior is subset of interior of fa for all a subset of x. In order to justify it, let us first assume it. And now we have to prove that f of a interior is subset of interior of fa. For it, let us take a subset A of x. We know that A interior is always subset of A, and therefore f of A interior is subset of f of A, or we can say that interior of f of A interior is subset of fa interior. But note that this map is an open map, and if map is open, we know that A interior, which is subset of x, this is tau open, and if this is tau open, So by openness of F of A interior is tau dash open. And if this is tau dash open, what we can conclude from here, that is interior of F of A interior is equal to F of A interior. That is F of A interior is subset of Fa whole interior. This is the proof of first part of this theorem. Moving ahead, now let us assume it and try to justify that F is open. Now, if we want to prove that this F is open function, let us take any A subset of X where A belongs to tau. Our motive is to justify that Fa belongs to tau dash, or just prove that interior of Fa is equal to F of A. This is equivalent to show that F of, that is interior of Fa, is a subset of Fa and Fa is subset of interior of Fa. Note that this first always hold because we know that for every subset P of y, P interior is always subset of, or P interior is always subset of P. In order to prove the second one, let us use our assumption. Assumption is given as F of A interior is subset of interior of Fa. But note that what we have taken. We have taken A as a tau open set, that is interior of A is equal to A. Therefore, this F of A is a subset of interior of F. That's the justification of this statement, and therefore interior of Fa is equal to Fa, or Fa is tau dash open, hence F is an open map. These are the references. That's all from this lecture. Thank you.